All right. I'm going to show you one more example, then I'll have you do one to practice and close out. So this one is one that they say to use the first derivative test, but I'm actually going to use both. I'm going to start with the second derivative test, and then whatever that doesn't allow me to find, I'm going to use the first derivative test. Okay. So first of all, I'm going to find the derivative here, the first derivative. So I always have to start there, either way. And so I would multiply 1/3 by 5, so that would be 5/3, and then it would end up being x to the negative 2/3, right? If I subtract 1/3 minus 1, and so that'll be negative 2/3, or we'll have x to the 2/3 in the denominator. Okay, and then minus 5/3 times 1, so it'll just be 5/3 in the front, and it'll be x to the positive 2/3, right? Okay. So that's my first derivative, and you could do a couple of things with this if you wanted to. You could convert this, you could kind of get a common denominator and bring it all together and make one fraction. I'm not going to do that just yet, but I will need to set that equal to 0 in a minute, but I'm going to find the second derivative first. I don't know why I keep starting out so far left and then needing to scoot over, but anyway, so the second derivative, remember this is a negative 2/3 exponent, so I would multiply negative 2/3 times 5/3, so that would be negative 10/9, and then we take away 1 from negative 2/3, so that would be negative 5/3, or excuse me, it would be positive 5/3 in the denominator, or I could put negative 5/3 in the numerator. Okay, and then here I'm going to multiply by positive 2/3, so that'll be negative 10/9, right? Because it's already negative, multiplying by a positive. But now this exponent is going to come in the bottom, and it's going to be a negative 1/3, right? All right, and so now for the second derivative, I want to set this equal to 0, right? Or excuse me, I want to set this equal to 0, the first derivative. So what I would do in setting this equal to 0 is I would add one of those or subtract one of those to get it on the other side, right? So probably the best way to go is to move this over. So it's going to be 5x to the 2/3 power over 3 equals 5 over 3x to the 2/3 power. Okay. And then what I would do is I would cross multiply. And so we're just solving. It's a little different because we have fractional exponents that we're solving for, but we also have a proportion, so we can cross multiply. But kind of be creative, use your skills. You're going to have some different type problems sometimes here. Here I would want to add these exponents since I'm multiplying the like bases, the x's together. I add the exponents. So 2/3 plus 2/3 is 4/3. Okay. And then on the other side, we'll have 3 times 5, which is 15. Okay, so then I can divide both sides by 15. Basically, those will cancel each other out, and I'll end up with a 1 over here, right, and an invisible 1 over here. So I'll have 1 x to the 4/3 equals 1. Okay, and then what I'm going to do now is I'm going to raise both sides to the reciprocal of this exponent. Okay. And that'll cancel out the exponent and turn this into just x. And then I can raise 1 to the 3/4 power, and 1 to any power is 1. So that'll just come out to 1. Okay. So we really only have one critical, well, let me take that back for a second. So this is our critical point as far as where f of x equals 0, right? F prime of x equals 0. Okay. But we also have another critical point here where we have a variable in the denominator. And whenever you have a variable in the denominator, you can take that and set that equal to 0. Okay, so you can say, well, 3x, when does 3x to the 2/3 power equals 0? And you can divide by 3, right? And you get x to the 2/3 equals 0 divided by 3 is 0. So then we can do the same thing and raise both sides to the reciprocal power. And these exponents cancel out, and you end up with x equals, and then 0 to any power is 0. Okay, so these are your critical points. Okay, critical point here, and critical point here. All right. So this is where f primed is 0, and this is where f primed is undefined. Okay. All right. So remember, for the second derivative test, really the only one that we can use for that is this one. So this one we'll have to do a different way, because if we plug in 0 here, we're going to get an undefined value, and so that doesn't work. So let's find the second derivative at 1 to see if it's positive, negative, or 0. And it'll yeah, positive, negative, or 0. So if I plug in 1 here, f double primed at 1, what I'll get is negative 10, and then 1 to any power is 1, like we've seen, so it's just going to be 10 over 9, because this will just cancel out. And then the same thing on this one, right? This will just cancel out, so it'll be 10 over 9, and so that'll come out to negative 20 over 9, and the keyword there is negative, so it's less than 0, so that means this is a maximum. Okay. All right. So we have that. Now we can evaluate this one, right? And we can use the first derivative test on this one, since we can't just plug in 0 to the second derivative. We can just find out what's happening on either side. Now I forgot one thing. When we raise both sides to the 3/4 power, when we raise both sides to the 3/4 power, we're basically taking the fourth root of both sides. So we have to take into account that we could have a positive or a negative, because if you raise this value to the 4/3 power, you're basically raising it to the 4th power and then taking the cube root. And so that you could have a positive or a negative here, just like when you square root both sides. So I should also do x equals -1 and evaluate that. Okay, so we'll do that. So we'll do f double primed at -1 as well. Okay, so if we do f double primed at -1, then what will happen is we'll get negative 10, and then -1 to the 5/3 power, since 5 is odd, the numerator is odd, it'll end up being a -1, so it'll be negative 10 over -9. And then same thing here, right? It'll be minus 10 over -9, so it'll end up being 10/9 plus 10/9, which is positive 20/9. And once again, the keyword there is positive, right? So since it's positive, it's going to be, since the second derivative is positive, it's going to be concave up, and that means this is going to be a minimum. Okay, so we actually have a max and a min, a max at 1, a min at -1, and then now let's figure out what happens in these intervals from -1 to 0, and then from 0 to +1. Okay, so we have to plug these values into the first derivative. Okay, so this is a little tricky because between 0 and 1 we're stuck with fractions or decimals, right? So you could plug in like 0.1 or 0.5 or whatever you want into here and just see if it comes out positive or negative. And so we'll just plug this into our calculator. So go ahead and plug in, let's do positive 0.1 here. Okay, so plug in 0.1 here, so it'll be let's do it here. So f primed at 0.1 is going to be, what is it, 5 over 3 times 0.1 to the 2/3 power minus 5 times 0.1 to the 2/3 power all over 3. Okay, so go ahead and plug that in your calculator and see what you get, and then let's do the other one at the same time. We'll plug in -0.1 f primed at -0.1, which is going to be same thing but with -0.1 in there. All right. Okay, so plug both those in, we'll get them, and we'll see what's happening on either side, whether it's increasing on both, decreasing on both, or if it's flip-flop. All right, so you actually get the same thing on either one. You get approximately 7.3769, etc. And so that means that the first derivative is positive on both sides. So it's increasing to the left of 0 and it's increasing to the right of 0. And so so this is not a critical point. Okay, so it's so this is neither. All right. And so those are our max mins, our critical points there. Let's look at the graph. So here's what the graph of the original function looks like. And so we can see here's where it's undefined, right? We have a vertical a vertical tangent line at that point, and so that's why the derivative is undefined there. But we can see at +1 that we do have a max, and we can see at -1 that we do have a min, right? Just like we suspected. All right. All right, so that's how it's done. So let's try one. Let's have you try one next.